Welcome to this video on the search problem in artificial intelligence. A search problem is about finding a path from a start state to a goal state. To do this, we define the state, the action we can take, and the rules that show how one state leads to another. The challenge is to explore these states efficiently and choose the best path to reach the goal. In this video, we will learn what makes up a search problem, how it is represented, and why it forms the foundation for many AI search algorithms. Let us begin and understand the basics of search problem in AI. Consider the problem of designing goal-based agents, and the agent has complete information about the world. Every action has a expected outcome, the state space is countable, and the environment is already fully defined. In such conditions, the solution to a search problem is a fixed sequence of actions that takes the agent from the start state to the goal state. Search is the process of discovering this sequence. Once the agent begins executing the solution, it no longer needs to monitor new percepts. This is called an open loop system. The maze and the right illustrate this idea. The agent starts at the designated start state and must navigate the pathways to finally reach the goal state using an effective sequence of actions. This forms the foundation of classical search strategies in artificial intelligence. A search problem is defined by a few essential components. First, we have initial state, which represents where the agent begins. Next are the actions, the possible moves that agent can take from any given state. The transition model specifies what happens when an action is performed. In other words, it tells us the result of applying a particular action in a particular state. Then comes to the goal state, which represents the condition the agent is trying to achieve. To evaluate different paths, we use a path cost, usually defined as the sum of non-negative step costs along the way. Finally, the optimal solution is the sequence of action that leads from the initial state to the goal while achieving the lowest total path cost. These components together form the foundation for representing and solving search problem in artificial intelligence. This example illustrates a classic search problem using the map of Romania. Our task is to travel from Arad to Bucharest. We begin with the initial state, which is the city of Arad. The actions represents traveling from one city to another along the connected roads. The transition model tells us what happens when we take an action. If we move from city A to city B, we simply arrive in city B. Our goal state is the city of Bucharest. Finally, the path cost is calculated as the sum of the distances along the edges we travel. This problem setup helps us understand how search algorithms explore the state space to find the optimal route. The initial state, the set of action, and the transition model together define the state space of a problem. The state space is the set of all states that can be reached from the initial state by applying any sequence of valid actions. We can visualize the state space as a directed graph where each node represents a state and each link represents an action that moves the agent from one state to another. Now consider the example Romania map. If our initial state is Arak and the actions allow us to travel between connected cities, then the state space is the collection of all Romanian cities that can be reached from Arad using the road connection shown on the map. In other words, the entire map of Romania represented as cities and the roads linking them forms the state space for this search problem. In the vacuum world example, a state is defined by two pieces of information, the location of the agent and the location of the dat. To understand the size of the state space, consider this. If there are two possible locations and each location can be either clean or dirty, we can combine these possibilities to determine how many distinct states the agent may encounter. More generally, if there are n possible locations and each location can independently be clean or dirty, the number of possible combinations grows exponentially. The agent has three available actions: left, right, and seq, which allow it to move between locations and clean dat. The transition model describes how each action changes the state. Moving left or right changes the agent's position, while the seq action cleans the dirt at the current location. This simple environment illustrates how agents perceive states, choose actions, and respond to changes in their environment. In the 8 puzzle, each state is defined by the location of all the tiles, including the blank space. The size of the state space grows rapidly with number of tiles. The 8 puzzle has about 181,440 reachable states. The 15 puzzle expands to nearly 1.3 trillion states, and the 24 puzzle skyrockets to about 10 power 25 states. The possible actions are simply moves of the blank space left, right, up or down, provided these moves are allowed by the puzzle's boundaries. The path cost is typically defined as 1 per move, meaning every tile shift has the same cost. This example highlights how such problems can become extremely large even with very simple rules.